All right. So my name's Han. I'm a grad student at BU, and just kind of joint work at Red Hat internship last summer. Um, so yeah, so we know that the Power is a first-class citizen in the cloud, and uh, and for a class of applications like in-memory key value stores. One result they showed was that actually if you were to plot the request rates over time in a day, there's actually a kind of a diagonal pattern where during certain times you have less load on your in-memory key value stores. And they found that you can actually try to save some power during this time by mainly changing the frequency on the processors. So that's one approach. And the other is by actually applying some sort of power limiting on some of these Intel processors that's been recently released. And in this case, we've kind of taken another approach. Instead of using the processors, decreasing the power there, we tried tuning another parameter on modern network cards. Actually, on a lot of network cards, there's a parameter there that lets you delay when the interrupt actually fires. So the interrupt gets fired from the card to your software so that you can start processing your packets, right? And on the particular card we're looking at, it has a certain range from 0 to like 1,000 microseconds, and you can statically tune that parameter however you want. There's a lot of policies that govern this value, and they're mainly targeted towards increasing your max throughput or decreasing your latency. But we've actually taken another approach and kind of looked like how we can use this to save additional power. And the general idea of why you want to manually increase this is the fact that by kind of delaying when you should be firing your interrupts, you're potentially buffering a lot of packets in your NIC. And we conducted a bunch of experiments on the MOC, mainly looking at Linux. And our setup is a 16-core Intel machine, and the kind of workload we're running is based off the same workload that was published in that paper, and we measured our power using a register on the provided on the processor that lets you actually measure how much power is being used by the processor itself. And we kind of compared it in a bunch of settings. So the first is we compared it using kind of like the dynamic algorithm that exists on modern Linuxes in terms of tuning this interrupt delay. We compared it with two approaches. The first is, what if we could statically increase this as high as possible without violating the SLA on this in-memory key value store? And the second one is, okay, by doing power limiting, how low can we get in terms of lowering the power usage on that machine before we violate the SLA? So the first one I'm going to show is kind of the Linux result. So the red line there is the SLA at 500 microseconds, and the x-axis is the throughput. So in the first case, you see that it's able to hit a peak about 800,000 requests per second at 16 cores. And the second graph shows the power usage at different request rates, so you can see that compared to doing the power limiting via the processor, we're actually able to save more power by actually delaying the interrupt as high as possible. And one effect of actually like really delaying your interrupt is the fact that you've effectively moved your 99 percentile latency just under the SLA. And because of the fact that you can tune this at 2 microsecond granularities, you're able to more fine-tune how you manage that. And the other case, so the graph on the left, one comparison point was, oh, okay, so in this case, we set the processor frequency to be the highest possible on the machine. And then the graph on the right is when we actually decrease the frequency to the lowest possible. And in this case, one interesting thing you can notice is the fact that the peak request per second rate on both, they're about the same. And this result actually revalidates some of the previous arguments for doing something like DBDK, right? Because the whole point of DBDK was the fact that your data plane was so expensive, you wanted something in between there to speed up your packet processing. And in this case, this kind of shows that because of the fact that even though we've dedicated more power or more frequency to the core itself, it's not able to increase its peak frequency. And the other interesting fact is the fact that in this case, actually applying like some sort of power limiting on top of this, even though when your processor is running at min frequency, the effect is negligible, right? And we're not 100% sure why this is the case. It could be the fact that the power limiting is doing it by reading like how much power you're using over a certain amount of time. And in this case, since your processor frequency is already so low that it cannot further decrease the power there. All right. And to kind of explain where these power savings are coming from, we collect a bunch of measurements using perf. So the first is just measuring like the number of instructions, right? Because you can think of this, okay, if I increase my amount of delay, that means I'm processing less interrupts. So that means I'm using less instructions to process interrupts. So that's why the instruction count is way less. The other one is also just. Oh yeah, sorry, I got confused. So this is just how many interrupts were fired. So because you increase your delay, your interrupts were fired less. Also, the instructions are less because you process less interrupts. And the other thing is the fact that you also spend more time sleeping. So in this case, we measured how many times the OS tried to go into different sleep states. And in this case, we found that with the policy of actually increasing your delay as high as possible, you're able to go into some deeper sleep states like C1E and C3. Okay, and then so I'm going to move on past Linux now, and the next experiment we wanted to see was, oh, what if we actually change the software stack completely? So in this case, we ported a library operating system, which is a multi-core library operating system that has a very heavily optimized memcached running on top of it. So and previous results shown by my colleagues was the fact that it was able to do like 1.5 times faster than Linux running natively even when you run this inside a VM. But in this case, we're actually running this bare metal on the hardware itself, and we wrote a device driver for the same NIC. So in this case, because so the obvious thing with this more optimized library operating system is the fact that you're able to achieve about 2.5x higher peak throughput compared to Linux. But the other interesting thing is the fact that you're able to use way less power even at the same request rates as Linux because of the fact that there's a much smaller kernel and there's less policies in general. But the other interesting aspect of this is the fact that the same mechanism of like delay interrupts, they still hold even when you change your software stack. And the other interesting result was, oh, what if we were to set the frequency the same way as before, where we ran the highest frequency in this optimized library OS and also set it at the minimum frequency. So in contrast to Linux, what happened here is the actual peak throughput of our library operating system actually dropped by half when we switched from the highest frequency to the lowest. And the argument here is kind of the same that I made with Linux, which is the fact that here, because we've optimized the data plane so much, because we're able to hit almost like 2.5x higher peak throughput, the fact that by decreasing the amount of processing or clock rates to the processor, right, you've effectively, that means your library operating system is more sensitive to the frequency of your processor. So in this case, our max frequency actually dropped, right? So the interesting result from this is the fact that, you know, if you're trying to move on to kind of library operating systems, these are kind of maybe additional things that you may not have thought of. So moving forward, so what I've actually done here is actually just shown kind of one parameter that exists on the NIC. And actually, if you look at the data sheet of this NIC, there's about 5,000 of them. They're all 32-bit values. And we've actually narrowed them down to about maybe 10 to 20 registers that actually affect the way your applications run. And in some sense, this is kind of similar to the previous talk about kind of exploring optimal knobs to tune in like a scientific application. Now another approach could be, oh, what if we could customize the way the hardware is configured for your specific application, right? All right, thank you very much.